Students, now we are going to see using Biot Savart's law what is the magnetic field at the center of a current carrying coil. Imagine you have a circular coil, okay, and an amount of current is passing through the coil. You want to find out what is the field at the center, what is the magnitude of field, what is the direction of field at the center of the coil. Okay, so this is a circular coil and it is carrying an I amount of current. And you want to find out what is the field at point O, that is the center of the coil. So what must we do? We take a small portion of the wire, circular coil. We find out that portion is the current element. We find out what is the field due to that current element at point O. Then what we do? We find to find the entire field effect at point O, we integrate. So first I am going to take a very small portion of the wire, circular coil, dl. Okay. Now from here I am going to draw my displacement vector r, which is also, it is the center, so it is the radius of the circular coil, and we are going to apply Biot Savart's law. Now what is Biot Savart's law? According to Biot Savart's law, the magnetic field at a point due to current carrying element is mu 0 by 4 pi I dl sin theta by r square. Now this is dl, so almost very small portion, it's almost a straight line, isn't it? And this is our displacement vector r. So the angle between them is 90 degree. So in this case, theta is equal to 90 degree. So equation becomes dB is equal to mu 0 by 4 pi I dl by r square. Okay. Now next we are going to find out, this is a field due to the current element. Next what we are going to do? We are going to find the field at point O due to the entire circular loop. So what must we do? We have to integrate. So the net field at point O is given by B is equal to integral dB, which is equal to integral of mu 0 by 4 pi I dl by r square. Now if you look into this diagram, you can see dl is the length, it is a constant value. I is the amount of current flowing through the conductor, that is also constant. R is the radius of the coil, that is also constant. So we can take all these constant values outside. We get this is equal to mu 0 by 4 pi into I by r square integral dl. Now when you integrate, what do you get? You have to get the total length of the circular coil, which means the circumference of our circular coil. So integral dl is actually what? 2 pi r, the circumference. So applying this we get dB is equal to mu 0 by 4 pi I by r square into 2 pi r. Got the common terms, this you get as mu 0 I divided by 2r. So the magnitude of magnetic field at the center of coil is mu 0 I divided by 2r. So next question, what is the direction? What will be the direction? What must I do? I must use my screw rule. Take a screw, you hold the tip of the screw at point O, rotate it from dl to r. What happens to my screw? It is going into the plane of the board, isn't it? So how will you note it? You note it with the number. So magnitude of magnetic field is given by, at the center of the coil is mu 0 I divided by 2r, and the direction of field is perpendicular to both dl and r into the plane of the board. Next we are going to find the magnetic field along the axis of a circular coil using Biot Savart's law. Okay, you are going to find, in the first case we found the magnetic field at the center of a circular coil using Biot Savart. Now what we are going to do, we are going to find out what is the magnetic field along the axis of a circular current carrying loop. Okay, imagine this is our circular coil. Okay, I am going to place the circular coil like this in the YZ plane. This is our XY plane. I am going to keep it, I am going to make the coil move inside. So, it will be in the YZ plane. My circular coil is placed in the YZ plane. And I wish to find what is the field along the axis of the circular loop at this particular point. Okay, I want to find out what is the magnetic field at a particular point along the axis of the circular coil. Okay. So, for that what will we do? Use the Biot Savart's law, and I am going to find out, this is my point, this is the tip of my pencil is the point. Okay. For that what I do? I take the, I divide my circular coil into small elements of length dl. Then I find out what is the field due to a single portion at point P. Then I integrate to find out the total field effect at that particular point. Now, my coil is like this. This is my axis. Okay. So, this is my current element. The top portion I am going to use. This small portion is my current element. So, what must I do? First, I have to draw a displacement vector from my current element to point P. So, this is my displacement vector. Okay. This is my displacement vector from the current element to the point P. Okay. Now, in our case, I have taken R as the distance from the center of the coil. Center of the coil is C. From the center of the coil to point P. R is the distance, not the displacement vector. Okay. And S is the displacement current element. Sorry, S is the displacement vector from my current element dl. S is the displacement vector from my current element dl to point P. This is my displacement vector, here is my current element. So, according to Biot Savart's law, the magnetic field at a point so this is my displacement vector and this is my current element, and according to Biot Savart's law, the magnetic field at a point P due to current element dl is given by dB is equal to mu 0 by 4 pi I dl sin theta by, instead of R, what is the displacement vector? S. So, I dl sin theta by S square. Okay. So, just see, next we have to find out what is the value of theta here. For that, you draw a tangent from dl. So, this is my tangent, okay, and this is my displacement vector. See, my tangent, my displacement vector. So, if you look, you can see this right angle. So, if my point is somewhere here, it won't change. So, the angle between dl and S is equal to 90 degree. So, my equation becomes dB is equal to mu 0 by 4 pi I dl sin theta by S square. So, I got the magnitude. So, next I am going to find out what is the direction of field, or what is the field at point P. What must I do? I have to take my screw, curl it from dl to S in a perpendicular, curl it from dl to S. You will find that the resultant vector is perpendicular to both dl and S. So, this is a resultant dB. Okay. Now, this angle, displacement vector is meeting point P at angle phi, and this angle is also, now you draw a normal, this angle also will become phi. So, what we do? The resultant vector can be resolved into two components. One is the component along the axis and one is the component perpendicular to the axis. The component along the axis is dB sin phi and the component perpendicular to the axis is dB cos phi. Similarly, this is due to the small portion at the top. Again, I am going to take a small portion at the bottom of my circular coil. You will get a diagram like this. You can resolve it to dB cos phi and dB sin phi. This is a resultant due to the current element at the bottom of my circular coil, and you will get a resultant like this, which you can resolve into 2 dB cos phi and dB sin phi. Now what is dB? It is mu 0 I dl by s square. Magnitude wise dB is same, but direction is opposite, which means the dB cos phi component gets cancelled, but the dB sin phi components get added up. Okay. Now we will get dB sin phi plus dB sin phi, that is 2 dB sin phi, which is due to the top and bottom portion of my circular coil. In a similar way, there will be several dB sin phi components. So what must you do to find net field? You have to add up all this. So instead of adding, what we use the integration method. So the total magnetic field at point P is, direction I will say later, is given by B is equal to integral dB sin phi. So I know what is the value of dB. It is mu 0 ideal by s square. Not what is sin phi. Take this diagram. Take this right triangle. Okay. This is theta phi. So what is sin phi? It is opposite side by hypotenuse, A by S. Also, using Pythagoras theorem, you can find out the value of S in terms of A and R. What will be S? S will be equal to root of A square plus R square. Now, what you have to do is you have to substitute the value. So, first I am going to substitute the value of sin phi in my equation. We get dB is equal to mu 0 by integral mu 0 by 4 pi I dl by s square into A by S, which becomes A by S cube. Now, if you look into this equation, you can find mu 0 by 4 pi is a constant, I is a constant, S is a constant, A is also a constant. So, what is varying? Our current element dl is varying. So, take all the constant terms outside, you get mu 0 Ia divided by 4 pi s cube integral dl, and on integrating, this is the circumference you are getting. So, it is equal to 2 pi A, where A is the radius of our circular coil. And on rearranging, you get magnetic field at that particular point P is mu 0 Ia square divided by 2 s cube. Cut the common terms, you get the equation like this. Next, we are going to substitute the value of S in terms of R and A to make our calculation more easy. Okay, so what happens? We get B is equal to mu 0 Ia square divided by 2 into, instead of S we have to substitute R square plus A square, the whole raised to 1 by 2 the whole cube, which is R square plus A square, the whole raised to 3 by 2. Now, this is the condition. The coil contains a single coil. Now, imagine your coil is made up of n number of turns. So, what change will happen to our equation? You have to write B is equal to mu 0 n, where n is the total, capital N. It is the total number of turns in our circular coil, Ia square divided by 2 into R square plus A square, the whole raised to 3 by 2. And in vector form, we have to express the equation, since it is a magnetic field, you have to express the equation in vector form. Now, you see, these two components are getting cancelled, only the sign component is remaining, isn't it? And it is directed along the radius. So, direction of direction of magnetic field at point P is along the axis, and it is this axis lying in the x-axis, this line is lying in the x-axis. So, we can write our equation as B is equal to mu 0 Nia square divided by 2 R square plus A square, the whole raised to 3 by 2 into unit vector I, which represents our resultant is along the x-axis. Now, next we are going to we are going to discuss about the special conditions. First one is, if imagine I want to know what is my magnetic field, what is the magnetic field at the center of the loop. So, what must you do? You have to put R is equal to 0 in the above equation, and if you put R is equal to 0, we get the equation as B is equal to mu 0 Nia square divided by 2A cube. If you cut the common terms, you get mu 0 Ni divided by 2a. Now, next what I am going to do is I am going to introduce area to my equation. Okay, you know that area is equal to pi r square, but our case r is not, we are not taking r, we are taking a as the radius of a circular coil. So, pi a square, and you substitute, you get B is equal to mu 0 n I capital A divided by 2 pi a cube, where capital A is the area and small a is the radius of a circular coil. Now next, imagine our point is lying very far away from the circular coil, which means R is very much greater than A. So you are neglecting A in the denominator. So you get the equation as mu 0 NIA square divided by 2R cube. On introducing the area to the equation, we get mu 0 NI capital A divided by 2 pi R cube, since pi A square is our area. Next, if the axis point, that is a distance r, is equal to the radius of a circular coil. So what will happen here? R will become equal to A. So our equation becomes mu 0 Ni divided by 2 raised to 5 by 2 into A. I hope you understood this derivation. Thank you.